All right, everybody. So here comes your next lecture. Gonna get us all set up here with a new screen. All right. Now, so we are gonna start talking about Chapter 7. And I realize that the assignment is due pretty soon, but it's pretty straightforward material. Most of it is just patterns in the periodic table. And hopefully you, by the end of this chapter, start to have like a growing appreciation for the deep organizational levels built into the periodic table. It's pretty fascinating. But first things first, before we really get into our first set of things, I want to revisit a topic of electron configurations for transition metals, and specifically ions of transition metals for transition metal ions. Okay, and there's a pretty simple rule, is that when you remove electrons from the neutral electron configuration, you pull from the highest N value first. Highest, you'll have to forgive me again, my handwriting is awesome. The highest N value first. Okay, so one of my favorite elements is vanadium. Okay, and I like vanadium because vanadium makes wonderful different shades of green elements, green minerals, depending on the oxidation state of the vanadium. But its neutral configuration is argon 4s2 3d3. Okay, so my highest N value is the 4. All right, so when I go to make vanadium plus, I take my electron out of that highest N value first before I take out of any other orbitals. So I'm going to end up with a 4s1 3d3. All right, let me fix this 3. It's a terrible 3. There we go. Okay, so if I go to vanadium 2 plus, I'm still going to pull from the highest N value first. So I've only got one 4s electron left, so I'm just going to leave that sucker out. So that becomes just 3d3. If I go up to vanadium 3 plus, now my highest N value is that 3d, so I start pulling from there. And that becomes 3d2. Okay? The reason that this works is that the 4s is slightly larger than the 3d and slightly lower in energy. There's a double L there. And slightly lower in energy. Okay, that's why the electron comes off easier. That electron is on the outside of everything in the 4s, and it's slightly lower in energy, so it's easier to pull off. Okay, the reason I wanted to talk about that before we move on is that that's going to come into play later. That whole 4s is slightly larger than the 3d thing. That's going to come into play when we start talking about atomic size of transition metals. Okay, so let's get into that topic of size. All right, so atomic size, okay, is a regular repeating pattern. In the periodic table. Okay, you might call it a periodic pattern. Okay, so there's three common ways to talk about atomic size. Right. One is the covalent bond. Okay, because we have three different kinds of bonds. We have covalent bonds, we have metallic bonds, and we have ionic bonds. Okay, so with covalent bonds, we're talking about, for example, the bonds in hydrogen peroxide. Okay, talking about a single covalent bond. All right. So with covalent, basically what we're doing is we're talking about, because covalent bonds overlap each other, right? So if I'm looking at the sort of electron cloud around those two oxygen atoms, they're going to overlap because they're sharing those electrons in a covalent bond. And so what we can do is we can go from the center of each and measure that distance as L. Okay? So 1/2 of L equals a covalent radius. All right. Next one comes out as let's talk about metallic bonds. Okay. So in metallic substances, there is no overlapping of those electron clouds. Okay, we just end up with atoms that just get stacked up in rows, nice and orderly, like this. They're not overlapping. So if I have some sodium, solid sodium, they just come out looking like this. And so what I can do is I can go from the center of each, same way. So I end up with the same sort of formula for a metallic radius. Okay, this is what we get for a metal lattice, which is a topic for another day. Okay, and then with ionic radius, which is our third kind, we're looking at, again, no overlap. And actually, I'm going to make that a little bit bigger. Aren't my circles nice? Okay. And here, I'm going to go from the edge of one to the center, and that becomes L. Okay? And with ionic, L is just the ionic radius. In this case, of sodium plus. Okay? So with all of this, how can we predict it? We've known for quite some time about approximate atomic radii, but we've only just recently gotten the technological ability to take images of atoms, right? So we haven't been able to really take good physical measurements of atoms. So how have we been able to predict it before now? Quantum theory of orbitals. Okay. So the idea here is that the atomic radius can be predicted by the size of the outer orbitals. Wow, my handwriting is really bad. Maybe it's because I'm using like a really tiny, skinny thing with my pen. Importance of this is, so we are talking about the valence electrons, and I think I just switched to too thick of a ink. Let's try the one in between. Okay. All right, so basically the idea is that the bigger the valence orbital, the bigger the atom. Okay? So the way we go about this with using quantum theory of orbitals is that we visualize it with a radial density plot. And we sort of looked at these a little bit in the last chapter. And these are probability plots, right? So if I have a plot, and let's see, on the y-axis I have the probability of finding an electron, and on the x-axis I have distance from the nucleus. So let's say if I'm talking about something that is a Z of 1. So we're talking about a hydrogen atom here, right? So that means it's a 1s, which means no nodes, right? Because remember, the number of nodes equals n minus 1. So if I do a radial density plot, it's going to end up looking like a nice little bell curve, okay? And my highest probability is right here at the top, okay? So I can estimate, well, this is a great dashed line. I can estimate the distance from the nucleus, right? And we call that 1a sub 0, or 1 atomic radii. And we figure out with calculation that, and we talked about this in the last chapter, is that turns out for a hydrogen atom, greatest probability of finding an electron is 53 picometers. Oh boy. Oh boy. Where'd you go? 53 picometers from the nucleus. Okay? And also with this, we find out that basically that probability fades away to basically 0 by about 5 atomic radii. Okay? So using this sort of model, we can start to estimate distance from the nucleus using our quantum mechanics. All right, if I'm looking at something that's slightly more complex, let's look at something that is for example, a 3p. So a 3p has 2 nodes. One of those will be a radial node, and one will be a angular node. Okay. So basically this is going to look like a dumbbell, and my angular node is the plane. So the plane runs right through the middle, and then my radial node is the 2p orbital that's on the inside, right? So my 2p will be on the inside, making a radial node. And that's not really all that like urgent that you understand all that, the radial versus angular. Unless you want to get into a quantum mechanics field, which you could. But suffice to say that with this two-node situation, when I draw my radial density plot, and we're going to put our percentage here and our distance down here. What this is going to look like is I'll get one node here, and it comes down to, right? So what this is right here, that's my inner node. Or not node, excuse me, lobe. So if we're talking about lobes of the 2p orbital, and then out here will be my outer lobe. Okay? So this would be my equivalent to my 2p, here's my 3p. Okay, because I've got them both there, right? And basically this is going to fade away at about 30 atomic radii, right? So my greatest area of finding an electron is going to be in that bigger, farther away from the nucleus 3p orbital. So the takeaway message here is that as the n value increases, the orbital size also increases, and my electron energy tends to increase. Okay? So a 2p is smaller than a 3p, a 4s is larger than a 2s. Okay, so the n value is a pretty good predictor of size. All right? So if we look at a specific example, so let's look at what magnesium solid looks like. Okay, what they figured out with the quantum mechanics is that the valence electron in the 3s for magnesium fades away at 0.3 atomic radii. Now hold on a second. Magnesium is significantly larger, like it's got way more stuff in it, I mean, than, for example, a hydrogen atom. Okay? Stop doing that. The idea here is that the 1s in magnesium is way smaller than the 1s in hydrogen. Why would that be? All right, so let's come back and take a look at what our hydrogen looks like. Our hydrogen, its 1s is at 53 picometers, or 1 atomic radii, right? But looking at magnesium, they figured out that its 3s fades away at 0.3 atomic radii. When we draw our radial density plot for that, and I put both of them on the thing, our percentage, and what we're going to get is that our hydrogen looks like this, right? And that is 1 atomic radii. My magnesium, well, let me finish labeling here. This one is the hydrogen 1s. The magnesium, on the other hand, is going to look like closer to this. right? So what is the cause of this? If there's so much more stuff in magnesium, magnesium has a higher atomic number, it's got more electrons, all kinds of things. Why is it so small in comparison? The answer is shielding. Okay, so shielding, we're going to find out, governs a lot of things about physical parameters of different elements. Okay, so magnesium has 12 protons. It's got a Z of 12, right? So that means 12 protons in there. And the idea here is that the higher the Z value means more pull on the outer electrons. Right, so remember, protons are positively charged, electrons are negatively charged. So when you have a greater attraction between those positive and negatives, what you get is smaller orbitals. Are smaller orbitals. Okay? So if there's a very strong attraction between the nucleus and an outer electron, that draws that outer electron closer to the nucleus, and you end up with smaller orbitals. And that the reason this all goes down is this, is that inner electrons shield the outer ones from that effect. Okay, so it's kind of like, I don't know, I did this example in lecture one time last couple of semesters ago, where, you know, you're in a crowded room, say at a party or a bar or whatever, and you see somebody that you're attracted to on the other side of the room, okay? But in between you and that person are all kinds of people walking past, standing in the way, and interrupting your view and attraction to that person across the room. Those people in between you are much like the core electrons. Those inner electrons are blocking that attractive person across the room from your attraction, okay? Because of course you're going to win no matter what. But that's the idea, is that the inner electrons of an atom shield the outer electrons from the pull of the nucleus, okay? So with magnesium, in between the 3s and the nucleus are a lot of electrons. There's a 1s2, a 2s2, and a 3p6. Okay? That is 10 electrons worth of shielding. Okay? So what we say here is that the 1s, the 2s, and the 2p in this example, the term that we use is that they have more penetration to the nucleus. It's kind of a funny term. Basically, to the nucleus, then the 3s. Basically, it means that they're closer. It's like getting more face time with the boss just because you're standing nearer to them. Okay? So what this is all leading to is a thing that is referred to as effective nuclear charge. And that's the important part, the effective part. So there's an attraction between the nucleus and the outer electrons. But how good is that attraction? Because we have to account for this shielding effect. So we're referring to the effective attraction of the nucleus. And we call this Zeffective. Okay? So Zeffective. And we have a way to calculate it. And I'm going to show you two ways. One is the way that I'm going to do it on tests, which is what I'm about to show you. And here in a few minutes, I'm going to show you another thing called Slaters Rules, which really is only good for one or two of the mastering chemistry problems. But I'm never going to use it on a test. But you still need to know it for mastering. And it's only in one tiny place in the textbook. So, but the way I'm going to ask for it is this. So Zeffective equals the atomic number, Z, minus S, which is the shielding electrons. Come on. And those shielding electrons are the core electrons. Okay, so remember when we did electron configurations, we talked about core versus valence. This is where this is going to actually come into real use here. Okay, so for hydrogen, you can calculate a Zeffective is 1, which is the atomic number of hydrogen. It has no core electrons because it only has one electron. So the Zeffective for hydrogen we say is 1 plus. Okay, and the idea here is that the valence electron, or in the case of the only electron, the valence feels this much pull. Okay, so as Zeffective goes up, the valence electrons are feeling a stronger pull. Okay, so let's look at what, so this is for hydrogen, has a +1. So for magnesium, the electron configuration for magnesium is neon 3s2, right? So my neon part, that's the core. And that has 10 electrons, okay? Look it up on the periodic table. Neon has an atomic number of 10. If there are 10 protons and it's neutral, it should have 10 electrons. So the core has 10 electrons because of the neon. And then the valence is that 3s2. I have 2 valence electrons in the 3s orbital. And magnesium has an atomic number of 12. Okay, so Zeffective for magnesium, the atomic number, which is 12, minus the 10 core electrons, gives us a Zeffective of 2 plus. Okay, so the idea here being is that the magnesium valence electrons feel 2 times the attraction than the ones in a hydrogen ion. If that attraction between the nucleus and the outer atoms is stronger, that means that everything gets pulled in closer to the nucleus, and we end up with a smaller radius. Okay? So this is our Z, and this is our S. Shielding core. Sounds like something out of some sort of a medieval movie. Okay. So how does this all fit into the periodic table? Right. Let's take a look at a rough periodic table. Here. Not a bad one. I'm getting better at drawing these over the years. Okay, so there's our periodic table. And what we find here is that here in my upper right-hand corner is fluorine. And fluorine is one of the smallest, it is the smallest main group element. Okay, excluding noble gases. Okay, so chlorine is the smallest, okay? So, but in general, if we start at the top of the table, we have smaller elements. And then as we go down the table, we get bigger, okay? If I'm on the bottom left, these are my biggest. And if I go left to right, they get smaller, okay? So if you can imagine, top is smallest, right is smallest. That's how we end up with fluorine being one of the smallest elements on the entire table. Okay, now why is that the case? So why does that trend hold that way? That going down the table, we have the same number of valence electrons. Right? Thinking about everything in the alkali metals in this first column, right? Everything here has a single valence electron, okay? And then in each case, the Zeffective is the same as well. Okay, because the core electrons in there in every situation will be the same as you go down. You know, so sodium has 10 core electrons, potassium has 18, rubidium has 36. Okay, so we always end up with a Zeffective of 1 and a single valence electron. But we're adding shells. Okay, and that's the important part about size getting larger going down the table, is that we're adding shells. We go from a 1s to a 2s to a 3s to a 4s to a 5s to a 6s, and everything underneath there. Okay, so like I said earlier on in this lesson, that the higher the n value, the larger the orbitals. Okay, so the moral of the story, and we'll do this in orange, atoms get bigger going down the table. Okay, and it's a virtue of same Zeffective, but just adding shells. We're not doing anything to the attraction. The attraction is staying roughly the same, but we're just adding layers to our onion, so to speak. Right? Going left to right, on the other hand, our core stays the same, so the shielding stays the same. Okay, because remember, the shielding is the core electrons. But as we go left to right, we are adding protons and valence electrons. And so what we see, because the shielding stays the same, if we're adding protons and valence electrons, we are increasing the attraction, or the Zeffective. Okay? It's kind of like, if you can imagine, like, and I love my medieval references. Imagine the Roman legions and their shield walls, and you've got, say, 10 guys in a shield. And first thing you do is you throw 10 barbarians at that shield wall and everything stays okay. And then you throw 11 barbarians and the shield wall moves back a little bit. And then you throw 15 barbarians at that 10 shield wall and it moves back even further and everything contracts and gets smaller. Okay, so that's what we mean by the shielding stays the same, but the attraction increases because we're adding protons and adding electrons. Okay, so going left to right, the atoms get smaller. Okay, so let's look at a couple of examples. So sodium. So it has an electron configuration that reads, well, that's interesting. Stop erasing things. Sodium is neon with a 3s1. Okay, we get 10 core for shield, like our Roman legion, right? In contrast, same row, chlorine has neon, 3s2, 2p5. Still just 10 core shield, right? So sodium is kind of like throwing 1 extra barbarian at the shield, and chlorine is kind of like throwing 7 extra barbarians at the shield. But let's come back to a slightly more scientific explanation than my Roman legion and calculate Z-effective. So Z-effective for sodium, we have Z of 11, an atomic number of 11, minus 10 core electrons, gives us a Z-effective of 1 plus. Z-effective for chlorine, we have an atomic number of 17, minus the same number of core electrons, means that Z-effective is 7 plus, meaning that there is much more attraction to the nucleus. Okay? Greater attraction between the nucleus and the valence electrons means that everything gets pulled in tighter. Another way that I sometimes like to think about Z-effective is like increasing sizes of magnets, right? If you take 2 little magnets out of like, I don't know, a tiny little speaker or something like that, 2 little refrigerator magnets, for example, and you put them together and they have, you know, a certain level of attraction. But if you take 2 much larger magnets, can't think of an example where you get larger magnets, but you know, simple carbon magnets versus neodymium magnets, on the other hand. Those larger neodymium magnets are going to stick together really, really strongly and be very, very, very tightly bound. So that's kind of the idea of between a Z-effective of 1 versus a Z-effective of 7. Right? So, for example, if I look at a couple of different atomic radius for rubidium, which is on the bottom left, it's element number 37, has an atomic radius of 250 picometers. Okay? Fluorine, on the other hand, on the opposite corner of the table, has an atomic radius of just 20 picometers. Okay? So big difference. Rubidium's got a Z-effective of basically 1, and it's got lots of shells underneath it. Fluorine has practically no shells inside, and it's got a Z-effective of 7. So you can imagine that with very, very little shielding going on, there's a big attraction between fluorine's outer electrons and its nucleus. So it pulls everything in really tight and really small and compact. Okay, so let's now transition in the notes. So this is page 6 of the notes where we've just stopped. And I want to transition into the other way to calculate Z-effective. Okay, and this part is not in the posted notes, so I'm hoping that all of you watch this video. Otherwise, if you need it, and I lost the page number, if you need it, the information about Slaters Rules is in the textbook. Slaters Rules are on page 262 in the closer look section. And it's the only place that you'll find them in the textbook, which is kind of annoying that mastering has a question where it wants you to do Slaters Rules. But the deal with Slaters Rules is that in a certain respect, it is a more precise way to calculate Z-effective. Okay. Now, like I said, Slaters Rules, I'm not going to ask any exam questions about. Okay, this is purely for mastering chemistry. Okay, but it is kind of cool. And the idea behind Slaters Rules is that it takes into account that not all of the electrons between the valence and the nucleus have the same level of shielding. They're not all protecting the same amount, right? And in fact, even some of the electrons in the valence shell provide a small amount of shielding. Okay, so it takes into account all that sort of stuff. So the way you deal with doing things with Slaters Rules, the first thing you want is to write out the full electron configuration, not the noble gas version. We want the full electron configuration, and this will become clear here in a second. Okay. So the next thing is that to know is that all but one of the valence electrons, all but one of the valence, get counted for shielding. Okay, and the reason for that is that one of the electrons in that outer level, on that most outer level, is the one that we're trying to figure out what the shielding is for. Okay, so one electron can't shield itself, is the idea. Okay, so what we're talking about is, as far as the valence, is that we're talking about the electrons in the same n as the row the element is in. Okay, and these get a shielding value of 0.35. Okay, so when I want to do this, what I'm going to say is that n, I'm going to say number of, wow, that's really terrible, number of electrons in that n value, electrons minus 1 times 0.35. Okay, this will all make some sense when I do an example. Okay, so part 3 here is that for all electrons in the n minus 1 value, all for the n minus 1 electrons, we give shielding of 0.85. Okay, and the idea here is that as we get in closer to the nucleus, as the n value goes down, we're getting closer to the nucleus. So the electrons closer to the nucleus shield more. Okay, so for n minus 1, we're going to say the number of electrons in that n-1 value times 0.85. Okay, so that's part 3. Part 4, I hope you're all taking good notes on this. For all the n-2 and lower, give shielding of 1. Right? So for n-2 or more, meaning n-3 or n-4 or more, we say number of electrons times 1. Okay. So the last bit is we sum all of this to get the shielding value for Slaters rules. Okay? And in the end, the Zeffective for Slaters rules becomes Z minus the shielding for Slaters rules. Okay? So all of that, blah, 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 blah. Let's do an example, okay? Because that will make things much, much more clear. All right, so example. We want to calculate Zeffective for silicon by Slaters rules. Okay, so first thing I need is the electron configuration, the full electron configuration. Right? So I'll have 1s2, 2s2, 2p6, 3s2, 3p2. Kind of cracks me up how sometimes my iPad will just arbitrarily make shapes out of my letters. Not really sure why it does that. All right, so coming back to our example. So silicon is in, I'm going to move this down. In, row 3. Okay, so that means same row, n equals 3, right? So for everything that is an n equals 3, that means these guys right here, that means I want electrons minus 1, because I've got 2 electrons here and 2 electrons here, so there's 4 total. That means that 4 minus 1, golly. Rats. Sorry, correcting things. 4 minus 1 for the n value. Okay? And then for my n minus 1, that's everything in the 2 right there. I've got 2 electrons there, 6 electrons there. That means I've got 8 in the n minus 1 level. And then right here, I've got 2 electrons in the n minus 2 level. Okay, so when I go to calculate the shielding via Slaters rules, I'm going to have what looks like this. I'm going to say there's 3 electrons in the n level that I need to worry about, and those provide a shielding of 0.35. Okay, so this is for my N level. And then I've got 8 electrons in my N-1 level, and they provide a 0.85 shielding. And then below that, I've got 2 electrons providing a shielding of 1. And this is my N-2 or lower. Okay? And so when I calculate that all together, I get S for Slaters rules equal to 9.85. Right? So when I calculate the Z effective, Z for silicon is 14. So Z effective for Slaters rules, 14 minus 9.85 will give me a Z effective of 4.15. Okay? So let's think about how we would look at that with the other method. With the other method, I would say Z effective, there are 10 core electrons, and an atomic number of 14, I would say 14 minus 10, I would say is the effective of 4. So Slaters rules gives us a way to calculate Z effective a little more precisely, but not in any big significant difference. Okay, so moving forward, I want to make this clear with my exams, I am not going to use Slaters rules. Okay, this whole thing about Slaters rules is to A, show you it exists, and B, give you the ability to answer the questions on the test. Or, excuse me, on the mastering. on the mastering. All right. So here we are. Coming in, we're just a little bit halfway through these notes. So I'm going to go ahead and call it quits and take a little break. I'll come back and finish with a second video.